for elastica we have the following function. We have the functional which we extremize or minimize, the following functional, which is the elastic energy from 0 to L kappa square ds, right, where kappa is my curvature with the most general formula that we have just derived, right. So, this is my elastic energy of the beam. Sometimes we impose that the length is also fixed, the length of elastica or the length of the material is also fixed. So, sometimes we also subject. So, sometimes we also subject to the isoperimetric constraint, to the constant arc length or isoperimetric constraint, arc length, the constant arc length constraint, right. We are going to look at all these classes of problems. Now, in my first case, let us look at a case of elastica with no arc length constraint, or a case for unconstrained optimization of elastica. Okay. So, the setup of the problem is as follows. We have, so case 1, we have elastica. Let me draw the figure and it might be clear. So, we have elastica which is clamped between two ends, right. So, we have elastica which is clamped here. So, let me call this end point as x 0. So, let me call this as 0 and I call this as x 1, right. Let me call this as 1, and we see that we are not imposing no arc length constraint, at this point. Okay. So, which means that this is a case where we impose fixed boundary conditions, fixed point boundary condition. We have that y at 0. Let us assume that the y coordinate at x equal to 0 is also 0, and so is the slope at 0, and we have, let us say that this is y equal to y 1 is 1. So, we impose the boundary condition y 1 at x 1, which is also 1, is 1, and we see that the slope at 1 goes to infinity. So, the slope becomes vertical, right. Okay. So, essentially this is a case of elastica between two frictionless guides, with fixed position, between two frictionless guide with fixed position and derivatives, but do not constrain, does not constrain the length. Okay. So, what we have is the following. So, we have the length L, which is also a fixed perimeter, but it is an unknown of the problem. So, let me have that. Let me describe the point x 0 is 0 and then x 1 is 1, and my arc length, let me impose that the arc length at the point 0 is 0, and of course, the arc length at x 1 will be equal to L. So, we are imposing our functional, we are writing the functional in terms of its arc length. So, my j of y, the elastica functional, will be integral from 0 to L kappa square of s ds. This is also equal to integral from x 0 to x 1 y double prime square divided by 1 plus y prime square whole cube ds, right. We see that well, right now this particular integrand is completely in the Cartesian frame. So, we can also replace my arc length element. So, this is also equal to integral of x 0 to x 1 y double prime square 1 plus y prime square whole cube times 1 plus y prime square dx, right. Okay. Or what we have is the integral from x0 to x1 y double prime square divided by 1 plus y prime square of 3 minus half, which is 5 by 2 dx, right. So, we have to extremize this functional. So, we see that this is a functional with second derivative. So, we are going to use Euler-Poisson equation to find the extremal. So, we use Euler-Poisson equation, which is going to give us del f del y minus d dx of del f del y prime plus d d x2 of partial f partial double prime is equal to 0. Notice that this particular, so what do we have? Notice that this particular integrand is independent, it is independent of y, right. This particular integrand is independent of y. So, we have that this quantity is 0, this partial f partial y, and we can integrate this whole, we can integrate this expression once with respect to x, right, to reduce the order of this equation from fourth order to third order. We see that this becomes the following. We have that partial f partial y prime is equal to d dx of partial f partial y double prime plus alpha, which is my constant of integration. Okay. So, let me keep it as it is, calling this as star. Now, notice we have a standard result from chain rule. So, from chain rule I can write down the derivative of f df dx. We can use chain rule to see that this is f of x plus f is a function of x, y, y prime, y double prime, right. So, f of x times y prime f of y plus y double prime f of y prime plus f triple prime f of y double prime, right. So, also notice again this particular integrand is independent of also x explicitly. So, it is independent of y, it is independent of x. So, which means that this partial is 0, right. If this partial is 0, I see that I can replace certain other quantities. Well, this is also 0, it is independent of y. So, this is also 0, right, and this one, this particular quantity can be replaced from this star to come to the fact that this is y double prime d dx of partial f partial y double prime plus alpha, right, plus y triple prime f y double prime, right. And students can check that this particular expression is nothing but the ordinary derivative with respect to x of alpha y prime plus y double prime partial f partial y double prime, right. Okay. So, notice, well, to see that we can differentiate with respect to x, we are going to get back this expression in the previous line here, which is underlined, right. Or we see that the partial, the total derivative of f with respect to x is the total derivative with respect to this quantity. We can integrate with respect to x again to come to the fact that f is equal to alpha y prime plus y double prime alpha del f del y double prime plus another constant, let me call this as minus beta. Okay. So, we have simplified our Euler-Poisson equation, and now we are ready to substitute our expression for the integrand small f. So, our small f is y double prime square divided by 1 plus y prime square to the power 5 by 2, and we see that once we do that, let me call this as double star So, from and call this as triple star. So, from double star and triple star, I see that I get the following expression. After simplification, I get the following expression, that kappa square, which is 1 plus y prime square to the power 3, which is also kappa square, is equal to beta minus alpha y prime divided by 1 plus y prime square to the power 1 by 2. Okay. Or I get that kappa, my curvature, is square root of this quantity beta minus alpha y prime divided by this square root 1 plus y prime square. Okay. So then, well, one way is to solve this equation. So, we need to solve this, right. The direct solution is not possible. So, we use some substitution. So, we substitute, again we start with the substitution y equal to tan theta, y prime equal to tan theta. So, I get that y double prime is equal to secant square theta d theta dx, and we see that my kappa comes out to be, we substitute all these expressions in kappa, we get that this is also equal to secant, well kappa is by definition y double prime divided by 1 plus y prime square to the power 3 by 2, and this is also equal to sin square theta by 1 plus tan square theta to the power 3 by 2 d theta, right, d theta dx, right. So, we get that kappa is equal to this, and we see that after simplification this comes out to be cos theta d theta dx. Okay. Or this is also equal to cos theta times dy dx. So, y prime of x times d theta dy, right. Or I see that y is equal to tan theta. So, this comes out to be sin theta d theta dy. Okay. So, from here I get set of two relations. I get that my dx d theta is equal to cos theta by kappa, and my second relation is dy d theta is equal to sin theta by kappa, where my kappa can be replaced by this particular quantity, which is cos theta divided by square root of. So, replacing this using this particular substitution, I get that this is also equal to square root of beta cos theta minus alpha sin theta, right, after using this substitution. Okay. So, this becomes, so kappa becomes beta cos theta minus alpha sin theta, and this becomes sin theta divided by square root of the same quantity beta cos theta minus alpha sin theta. So, the crucial part is now all we need to do is to integrate this quantity on the right hand side with respect to theta to get the parametric representation of our extremal. Now, I am going to quickly show the way to solve. Well, before we do that, we have used the substitution, and we must also show what is the corresponding boundary condition for this substituted variable. Notice that y of 0 is 0 and also y prime 0 is given to be 0. This is my regular boundary condition. Now, that is only possible, we have substituted y prime is equal to tan theta. That is only possible when theta is equal to theta. So, theta 0 is equal to 0, and then we also have that y prime at 1 goes to infinity, implies that theta 1 is pi by 2. So, my theta lies between the range 0 to pi by 2 in order to satisfy the boundary conditions. Okay. So, then in order to solve, let me call this setup, let me call this set of equation as R1. So, in order to solve R1, we now start substituting, we choose R1 is equal to, so in R1 we choose our constant a to be 1 by square root alpha square plus beta square, and we choose my second constant b to be cos inverse of beta divided by square root alpha square plus beta square. And once we use that, our set of equations reduces to the following new set. I am using another variable phi to be theta plus b by 2, and my new set of equations are as follows: 2a cos 2 phi minus b divided by square root of cos 2 phi, and my second equation is d phi dy d phi is equal to 2a sin 2 phi minus b divided by sin square root of sin 2 phi. And we can see that this equation reduces to some constant C1 times square root of cos 2 phi plus another constant C2 times sin 2 phi divided by square root of cos 2 phi, right. And then the second integral, the second differential equation reduces to the following form: sin 2 phi divided by square root of cos 2 phi minus another constant of square root of cos 2 phi, right. All I need to do is to integrate this. So we note that in order to integrate, note that we have the following. We have that this particular integral, we have two basic integral, one is the integral of this quantity, the other is the integral of this quantity, right. The integral of this quantity sin 2 phi by square root of cos 2 phi is known as the elliptic integral. Well, this, not this one, this one can be directly integrated. This turns out to be negative square root cos 2 phi. I can integrate this right away, plus a constant of integration, okay. And the second integral, which is square root of cos 2 phi, this can be written, the answer can be written in the form of an elliptic integral. In fact, this is the definition of elliptic integral: square root of cos 2 phi d phi. This is the elliptic integral of the second kind, phi comma square root 2. So this is my elliptic integral of the second kind, elliptic integral of the second kind, which is this one, okay. So then let me write down the final answer. The final answer that I get, x of phi is equal to C3 plus C1 elliptic integral e of phi comma square root 2 minus C2 square root cos 2 phi, and y of phi is equal to C4 minus C1 square root cos 2 phi plus, well, minus C2 elliptic integral of phi comma square root 2. Now this final result is in the form of 4 constants C1 to C4, and the way to derive is as following. It's not easy to find all these constants because we have done lots of substitutions, but note that my phi, the original phi was an angle with respect to the intermediate constant b, and these are, again, this is a transcendental equation in general, transcendental equation, right. And we know that now, so the direct solution is not possible, direct solution not possible, but what we do is the following. What we do is, look at this, that we need to properly, so we know that cos varies from -1 to +1, but in order so that the square root is defined, this square root is well defined if the argument inside the square root is positive, or I have that my angle 2 phi is from minus pi by 2 to plus pi by 2, right, or I have that phi is from minus pi by 4 to pi by 4. So, that is my range of the angle that phi can take. However, since I have already derived that theta was from 0 to pi by 2, this is something that we had to begin with, right. And so, this was the larger range of phi. Phi will be certainly within this range. Now, also we have that phi is centered around 0, right. So, phi is, so we have a solution. Why we have a solution E1, so E1 with respect to phi equal to 0, right. So, it is centered around 0, well centered around phi equal to 0, which means that this situation is only possible when this range is further. So, only this is only possible when this range is further restricted to phi from minus pi by 8 to pi by 8. Look, we need a range which is centered around 0, but we also had to satisfy the constraint that the original angle theta is from 0 to 2 pi, right. And so that is possible when phi has a much more restricted range. Now, all I need to so all that is left is we have to evaluate x at pi by 8. So, my boundaries are from minus pi by 8 to pi by 8, and we also had the set, note that we had the boundary conditions y of 0 is y of 1 is equal to 1, right. So, well, what we had was y of 0 is 0 and we had y of 1 was 1. From here the corresponding set of boundary conditions are x at pi by 8, which is also at, well, so pi by 8 corresponds to the minus pi by 8, the left hand side limit of this interval corresponds to the point 0. So, x at minus pi by 8 is y at minus pi by 8, that must be equal to 0, and the second set of point x at plus so x at plus pi by 8 is 1, and we have y at plus pi by 8 is also 1. That is the second set of boundary condition that we have. So, we have 4 equations and we have 4 unknowns C1 to C4, and hence our problem is quite well defined. Now, before we wrap up this example, I just want to highlight how does the shape, so the solution figure. So, how does the shape of my elastica compares with the shape of a unit circle? We are talking about the solution in the first quadrant, right. So, in the first quadrant, if we were to plot a unit circle, if we were to plot a unit circle, it will have the following shape, right. And on the other hand, if we were to plot the shape of a elastica, it comes out to be quite close, right. So, this question is, why didn't we just use the approximation in such a way that simplifies our problem and gives us a shape which is close, but quite close to unit circle. It seems quite intuitive that the shape, since it is quite close to a unit circle, should have followed a functional which is very similar to the one that gives unit circle as the extremal. But on the other hand, if we plot our elastic energy, which is F, which is kappa square, right. Once we know the solution, we can definitely plot the elastic energy. Now, for a circle, so this is my y equal to 1. So, for a circle, the elastic energy lies parallel to the y axis, right. So, this is for a circle, and for a elastica, this is purely a curve which is not parallel to the x axis, right. So, it seems that although the shape of, so this is my unit circle, the shape is very similar to the unit circle, my elastic energy tells or paints a very different story, and hence and hence the solution to this problem is non-trivial, right. So we can extend our solution methodology to another case which we are going to look at in our next lecturing session. So thank you very much for listening. So in our next lecture, I am going to talk about the case of the variable endpoints where both x and y are also varying. We will also complete this example of Lastica by looking at another test case where we impose the length condition or the isoperimetric constraint. So thank you very much for listening in this lecture. Thank you. Okay, well, the last topic of this lecture is we will continue our discussion on the case of Elastica. We are going to look at another case of Elastica where we impose the length constraint. So here we have a case of Elastica where we are going to impose our length constraint. So let me call this as x1 and let me call this the total length of the Elastica is L. So this is the case of Elastica with fixed length constraint. So now the set of conditions that we have is on the side on one of the endpoints x naught equal to 0. So I have x naught is equal to 0 and my second endpoint x1 is not known, but at x naught equal to 0 I have the condition y at 0 is equal to y prime at 0 is 0. So we impose the position coordinate as well as the slope equal to 0, and at x1 where x1 is an unknown, so we do not know what is the position the y coordinate at x1, we call this as y1, and but we also have that the slope approaches the vertical or the y axis. So the slope eventually becomes parallel to the y axis. So we do have the slope information at this second point. Now so this y1 is an unknown of the problem. So we have to use our natural boundary conditions. So we use natural boundary condition, right. Okay. And further we have the length constraint. We impose the length constraint, which means that my integral of ds from 0 to L is equal to L. Okay. So we fix our length and impose the length constraint. So which means that the functional for which we have to, the function for whose functional has to be optimized is the following. So the function f is, well, I directly write the functional. The functional f is 0 to L kappa square ds plus lambda times. So lambda is my Lagrange multiplier, lambda times ds from 0 to L, right, where this constraint is nothing but integral from 0 to L square root of 1 plus y prime square dx, right. Okay. So then I can certainly start by looking at so the boundary conditions that I have, the natural boundary condition that I have is the following. Well, let me just write the final simplified form of this functional. This becomes integral from 0 to L y double prime square divided by 1 plus y prime square whole cube. So that is my kappa square, and times well plus lambda times square root of 1 plus y prime square dx. So this is my integral that I am trying to optimize. So my natural boundary condition, so this is my f, my small f or the integrand, and my natural boundary condition are as follows. We have to use the condition for higher order derivatives. and we see that this imposes the following constraint: partial f partial y minus d dx of partial f partial y prime times eta plus, so this is evaluated at x1, and times plus eta prime partial f partial y double prime imposed again at x1, this is set equal to 0. So, we individually set each of these quantities to 0 to get to natural boundary condition. Okay. So, then the solution, I am going to right away use our solution to the previous test case. The solution to my Euler-Poisson equation from our previous example is directly found out to be del partial f partial y prime is equal to d dx of partial f partial y double prime plus alpha, that is from our previous case. Okay. And finally, we have that well, note that this is nothing but equal to 0 at x equal to x1. So, this is nothing but from the natural boundary condition, this is 0, and also we see that this quantity is also a well, what we have is the following: this quantity this minus this quantity is equal to 0 from our natural boundary condition, at x equal to x1. So, that brings in the conclusion that my alpha will be identically equal to 0, right. Okay. So, alpha is a constant and that will be 0. So, which means that from my previous case I can directly write the solution to the Euler-Poisson, right, from previous case with alpha equal to 0, and we have the introduction of a new constant lambda. We see that our equation reduces to the following form: my f is y double prime square 1 plus y prime square to the power 5 by 2 plus lambda times square root of 1 plus y prime square. For this f, my equation reduces to the following: 1 plus y prime square in the denominator is equal to lambda plus beta times 1 plus y prime square to the power 1/2. Notice that the quantity on the left hand side is kappa square, and again we use the same set of substitution to solve this equation, that is y prime is equal to tan theta, and then again we are going to get a set of two equations. So, this is again from the previous example. We are going to get a set of two equations: dx d theta is cos theta by kappa, which is in this case coming out to be cos theta by square root of lambda plus beta times cos theta, and dy d theta is equal to sin theta by square root of lambda plus sin theta. And then the solution follows a similar methodology. We again use a similar set of substitutions to come. So, let me write down the final solution. The final solution for this case comes out to be the following. So, x of phi is gamma times 2 elliptic integral of the second kind of phi comma k minus elliptic integral of the first kind f of phi comma k, and the parametric representation of y is 2 times gamma of k 1 minus cos phi, where my angle phi is such that sin k times sin phi is sin theta by 2, and also the constants k is square root of lambda plus b by 2 beta, and my constant gamma is square root 2 by beta. So, that completes the solution to this constrained Elastica problem.